Thanks, Jason. Yeah, I have no idea what that noise was. Yeah, and the lecture will be recorded. So after that spiel that wasn't recorded, then there are some practice problems on here. They're in the textbook. There's lots of them. I'm going to be starting to post more assignments. So I have 3 assignments posted. I'm going to start posting some more. You're not going to be able to do all the questions yet. That's okay. You can do what you can, or you can read ahead and try and do the stuff that you can't do, which is cool too, because you really do have all the tools you need to do everything that we need to do for the rest of the course. Now we're just decorating for the rest of the course. Okay. So we're going to really get into the role of the idea of the conventions that we're using for this. So let's say we've got an alkene. That's an alkene. What is it? It's, I guess, 2-methylpropene, if anyone's keeping track. I'm going to use reaction arrows. Reaction arrows are vertical or horizontal arrows that are double-headed. They're kind of normally in the middle of the structure, and they're indicating that I'm doing a transformation. I will generally write reagents on the top. And then we'll have conditions on the bottom. Oops, and I did not want to do that. I wanted to just change my ink color. I don't know. THF, which is a solvent. So there might be temperatures, there might be solvents, there might be other things on the bottom. Normally you need to worry most about the stuff on top, though we'll see lots of examples where you need to worry about the stuff on the bottom too. You got to worry about all of it because it's all there for a reason. Otherwise, why are you adding it to your reaction? So we are in a Latin-derived language, and so we generally work from left to right and top to bottom. We will generally draw products on the right-hand side of the arrow. So products, reactants, reagents, conditions, terms that I'm going to be using. Now, reactants and reagents, a reactant is normally defined as something which is showing up a lot in a product. Like the atoms in the reactant are showing up in a product, but it gets kind of iffy defining reactant and reagent. And a reagent is something that helps you turn the reactant into the product. But there's a lot of reagents that are more like reactants and reactants that are more like reagents. And so I'll use the two terms more or less interchangeably. It's things that get involved with making the product. But the reactant, the most important reactant, is also called the starting material. And the starting material is the most important reactant, where most of the atoms are showing up in the product. Okay. So, this is kind of like the anatomy of a reaction. And so if you can refer back to this if you need to. Now, there's no mechanism here. I've just drawn a reaction, and I've done this double bond, and suddenly there's HCl, and then there's an HCl appearing on the double bond, and double bond's gone, and something's happened, and things. So now we're going to basically spend the rest of this course talking about the stuff that is happening between the left and the right structure there. So let's think about that. So there's a lot of ways we can think about what's going on here, and we're going to basically pull this reaction apart in about 2 to 3 different views. So the first one's the simplest one, and this is kind of how you're going to be sketching it out for most of the course. And that's that you're going to think about, okay, I have a double bond, and I have an HCl, and I'm going to be drawing reaction arrows. Now, reaction arrows go from electrons to where the electrons are going. We've already talked about this with the acid-base stuff. That's what we're going to do here. Now, this is essentially an acid-base reaction. what we're doing is our base just happens to be a double bond. So we're going to talk about exactly what's going on in the next few minutes, but we'll start there. And I'm going to use that double bond, and my electrons in that double bond are going to go attack the H. Now, why are they attacking the H? Well, we know that that bond is polarized. That HCl bond is very polarized, right? With delta plus meaning slightly positive, delta minus being slightly minus. The chlorine is pulling the electrons towards it. So on that bond, that H is quite positive. It's almost an H plus. And we know that, you take HCl, you dump it in water, it dissociates into H plus Cl minus. It's a strong acid, dissociates completely in water. And because it dissociates completely, that tells you that that HCl bond can't be super strong. It's a covalent bond, but falls apart without too much motivation. Cool. Okay. Notice that I'm drawing the bond starts in the middle of the double bond. The arrow starts in the middle of the double bond. Being really clear that I'm using the arrows, the electrons in the double bond to attack the hydrogen. The arrow is double-headed. And what that means is that 2 electrons are moving. But now I'm making a new bond to hydrogen. Okay. Well then, hydrogen can only make 1 bond. So I've got to break a bond to hydrogen. Stick the electrons onto the chlorine. And I'm going to draw my product. This is an intermediate of the reaction. It's not the product of the reaction. We're not done yet. But we've drawn another valid Lewis structure. We've gone from one valid Lewis structure to another valid Lewis structure. We're not done yet. Okay. Now, you're looking at that and you're thinking, well, you got 2 electrons, you got 2 carbons. Why am I making the top one and not the bottom? And this comes down to what we finished off last class talking about, which was hyperconjugation. So, just like in acid-base reactions, when you're trying to break down equilibrium, figure out what's going on, here we're always thinking about where does the charge want to be. So I got my eye out for resonance. I've got my eye out for induction. I'm thinking about which atom these things are going to be on. And when I'm looking at them going, okay, everything's carbon, there's no obvious induction or resonance effects here. So walking down this list, I arrive at hyperconjugation. Again, I'm going to itemize this list again with respect to these kinds of reactions and how we're going to favor things. And we know that a tertiary carbocation is far more stable than a primary. Talked about this at the end of last class. And that's because you have all these hyperconjugation effects from all these carbons adjacent to it. So, does not exist, or does not happen, I guess is a better way to put it. So we only get this top one. We get the hydrogen adding to that primary carbon because it gives us the carbocation at the tertiary carbon, which is where it wants to be. Okay. Now, we've got a negative charge. We've got a positive charge. They might be reasonably close together. They are both things that we don't really want because we don't like charges. So I'm drawing the arrow going from the chlorine, from one of the lone pairs on the chlorine, to the carbon with the positive charge. And that takes us to our product. Okay. So that's one way of looking at it. Another way of looking at what we just saw is let's think about the orbitals. So we got a pi bond. And, that's making a pi bond, two p orbitals on the carbons and the carbons. And we got two methyl groups on one of them. And then if we think about this, we've got an H and we've got a Cl. And that Cl, these little nubbins here are the back end of the sp3 orbitals that are on the chlorine. I'm not going to draw all of them in. I'm going to actually just kind of start leaving them out because they're irritating to draw in, and you don't have to either. So, and then, if we're sort of counting, we can sort of draw one electron each of those orbitals. But they're, we're drawing linear combinations of atomic orbitals. So you need to remember that it's not like those two orbitals are kind of touching. It's that they've combined to make a new orbital, but we just haven't drawn it in for simplicity's sake. Now, what is this? Well, this is the bonding orbital. This is a sigma orbital on the chlorine hydrogen. But whenever you have a sigma orbital, you have an antibonding orbital, you have a sigma star orbital. Okay, what does that look like? Well, what it means, we know, is that you don't have electron density between the chlorine and the hydrogen because it's antibonding. So all the other orbitals are the same. But we sort of have the equal but opposite. And I'm going to draw this as out of phase with the s orbital. So now we have no electron density between the hydrogen and the chlorine. I'm turning on my camera because I'm gesturing with my hands as well. So, the hydrogen and the chlorine, there's nothing in between them. In a sigma orbital, that's where all the electrons are. In the antibonding orbital, they're not there. If you put electrons into the antibonding orbital, you break the bond. Maybe you see where this is going. So if we think about going back to this guy, oops. We got two electrons, p orbital. Electrons move around. It's kind of like what they like doing. Another way to draw this same molecule, kind of sort of like a resonance structure. They're not Lewis dot structures we're drawing here, so they're not really resonant. Well, actually, it is a resonance structure. It's exactly a resonance structure I'm going to draw. Is what if, given moment in time, for whatever reason, both of my electrons are over on that left-hand p orbital. Okay. That's equal to me just having drawn that, the lone pair on that carbon out there. That's a resonance structure, right? Like, it's a silly resonance structure. You got charge separation, you've broken a bond, but it's a resonance structure. And so you can kind of think of this as a lone pair on that orbital. And again, this is the direction the electrons would prefer to go because we want that carbocation on that central carbon because of all the hyperconjugation. And we want the carbanion, the negatively charged carbon, on the less substituted carbon, again, because it wants to avoid all that hyperconjugation. Like, the positive charge is happy, the negative charge is happy. Well, they're not really that happy, but they're happier than they would be if they switch places. So now what we can do is we can imagine that this orbital, this p orbital, has got extra electrons. This sigma star orbital is missing electrons. And so what we can do is we can combine this p orbital with that sigma star orbital to make a new bond. And what that's going to do is it's going to transfer electron density into the sigma star. And as soon as we do that, we break the bond. We break the hydrogen-chlorine bond. And so another way to think about this is what you have the p orbital attacking the hydrogen by putting electron density into this antibonding orbital. So I guess I'm attacking the wrong hydrogen. I guess I should attack the hydrogen that's in the antibonding orbital. It's the same hydrogen, of course, but just different energy state. And when we do that, we break this bond because we've now put electron density up into that sigma star. Now, as we do that, we're breaking the pi bond. And so this is no longer going to be a p orbital. It's going to switch to being sp3. But the p orbital we left behind, that carbocation, is still a p orbital. This guy's gone. He's got some hydrogens attached to it, which I just haven't drawn in. I do not want to draw it that way. That makes me feel queasy. This whole thing might make you feel queasy. So it's now got a new bond to the new hydrogen, and these are the old hydrogens. I'm going to just draw the new hydrogen in a slightly different color. By slightly different, I mean I'm doing it in green. And so we can think of these in two ways. Now, this is a really complex way of thinking about this. You don't want to be kind of ducking into this every single time. We're going to kind of duck into this occasionally. Mostly we're going to do what we did in the first slide. And that's fine. If all you do is understand it on that level, that's cool. That's absolutely fine. You can score 100% in this course. So there's no electrons in. So what I've done is I've drawn in the lone pairs. Anita asked, can you explain where the 8 electrons are in the antibonding HCl? This is where we're mixing multiple things and we're starting to get confusing. So I'm kind of keeping track of these guys as placeholders. What I'm really looking at are those orbitals don't really exist in the sigma. They're lower in energy than the sigma. The sigma bond is this one I'm looking at. The sigma orbital is that one I'm looking at. And then there's no electrons in it in the sigma star because they're only in the sigma. I'm just drawing in the lone pairs to keep track of them, just so that we're all clear that those orbitals are there, but they're not actually the sigma orbital. The sigma orbital is that one that I'm worried about. Yeah, it's just keeping track. This guy here, Nicole? Yeah, so this is the result of the reaction. So once this guy with the 2 p orbitals and double bond reacts with the sigma star, it makes this. So this is the product. This is the reactant. This is the reagent. Does that make a bit more sense? Cool. Okay. So, and this brings us back to this idea that a carbocation is an empty p orbital. And that's exactly what a carbocation is. It's an empty p orbital. So when we have chlorine coming by, yay chlorine, it's our hero. It sees that empty p orbital. And it goes, well, that's kind of sad. It's lonely. And the chlorine can either come to the top lobe or it can attack the bottom lobe equally. Doesn't matter, it'll do one or the other. And it's got a 50-50 shot of both. This is going to matter coming down the line. Right now, who cares, all the same. It's going to matter in a couple of classes because that's going to give us stereochemistry. But right now, it doesn't matter whether it attacks the top or the bottom. We get the same product. And that product is, I'm drawing one of them, is that guy. Though they're all the same because this is not an asymmetric carbon because it's got 2 methyl groups attached. The 8 electrons are in the molecule as a whole, but they're not in the orbital. We're just talking about this specific sigma bond. There's only 2 electrons. Everything else is lower in energy, and I'm not worrying about them. I'm just looking at the electrons in this particular ClH bond. I'm not worried about the lone pairs on the chlorine. We're just going to sort of isolate bonds at these, because if we try and consider all the molecular orbitals on all the molecules we're going to draw, we're going to make our minds explode. So we're going to think sort of about something. Actually, they're called frontier molecular orbitals. They're orbitals. They're the highest energy orbital that has electrons in it, and the lowest energy orbital that doesn't have electrons in it. And that's where reactions occur. Okay. Cool. So let's take a look at a different example. So I'm going to change my color because I really, really hate the screen. Hi, do you want to do chemistry? Okay. Yep, you're popular. There we go. Zoe's here to do chemistry too. She's meeping at me. Okay, so if we have a different alkene. Yeah, that was different ways to show the same reaction. So one way we just drew arrows, one way we took a look at what was going on with the orbitals. So let's think about HBr. Again, we use a different solvent, dichloromethane. It's a really good solvent. Somebody tried to clean their carpet with it recently because it's very good for that. A couple people die every year because they put themselves in a really poorly ventilated garage with dichloromethane, and it evaporates at 30 degrees. So if you're there in the summer, it will evaporate and you go to sleep and you basically die from inhalation. But it dissolves everything. Well, a lot of things. So you find it in a lot of paint strippers and stuff. And we use it a lot in organic chemistry because it has a nice, really nice boiling point. It's a lot of fun to work with. So again, now we think about this guy. And again, we've got our nucleophile. You can also think of it as a base. And this H is our acid or electrophile. So an acid and a base are a specific subset of nucleophile electrophile where we're dealing with attacking H pluses, generally. With the way we're talking about this, I'm going to talk a lot more about nucleophile and electrophile because it's more general. But you can also think of this kind of as acid base. So double bonds got the extra electrons. We want to go out and grab an H plus. And we just saw this. We think about how this HBr bond is polarized. And I really hope you can generalize from HCl to HBr. Oh, that's fun. I'm not getting any rain right now, but I can hear the lawnmowers out there. The lawnmowers of LaSalle. They're always going. So we can use a double bond. We can attack this guy. And again, we can think about the H goes on one of those carbons. The positive charge goes on the other. I'm looking at the 2 carbons, and I think one is secondary and one is tertiary. If you can't remember what those words mean, go back to your notes from last class, which is great because you can now actually go back and listen to my droning voice. And so we put the positive charge on the more substituted carbon. Why? Because of hyperconjugation. Again, we're not seeing any resonance. We're not seeing any real induction effects. There's no real preference under anything else. We're really driving this by hyperconjugation. That leaves us with a Br minus. What does this guy want to do? minus goes to plus. And I've arbitrarily drawn it on the bottom. I could have drawn it on the top, that's fine. It doesn't matter because this is not an asymmetric carbon, because that carbon is attached to two of the same things, and that's going around the ring. I think we did an example like that a couple classes ago with a spiral bicyclic thingy where the two rings were the same with whether you went left or right. It's the same thing here. Okay. We can mix this up a bit. A little bit. Not a lot. Not going to go crazy here. Let's do H2SO4 in water. So here our solvent is water. And this is one of those things where you have to look for what's under the arrow, because you need to keep your mind on the options. So let's think about this. I'm putting a reactant above the arrow and the solvent under the arrow. Normally that means there's an awful lot of solvent and not very much reactant. If you kind of want ratios, like molar ratios, you're normally on the order of 1 to about 10,000. Kind of the ratio number of moles of those two things. That's pretty general. Normally, actually, that's pretty concentrated. Normally, it would be 1 to 100,000. But let's say it's 1 to 10,000. Okay, well, let's think about what sulfuric acid is. I'm sure you covered this in Gen Chem, but just in case it's been a little while, it's this guy. And we know that sulfuric acid is a strong acid because it's sulfuric acid. Like the whole acid thing gives it away. And you can dissolve bodies in Terminator movies in it. And so sulfuric acid, as we know, in water is going to be in equilibrium. No, we're doing this in water. The other ones we've done in organic solvent. Not suddenly we're in water. With hydrogen sulfate. And then you're also going to you're going to be able to deprotonate the other proton too. That's also going to be in equilibrium with its conjugate base. But who cares? We don't need to worry about that. This gives us everything we need to work with. So we got this H plus. I know what to do with the H plus. I've just done it twice. Let's do it again. Don't need to get fancy here. Note, I'm kind of drawing a few reactions over there and I combine them. That's fine. Whatever you need to do to keep track of things, the arrows keep track of it for you. I didn't need to draw this equilibrium there. I could have just grabbed the hydrogen directly. That would have been perfectly fine too. We're going to see lots of examples of different ways of doing it. Again, I know I'm going to put the positive charge on the tertiary, not the secondary. And again, I know that there's no induction, there's no resonance. I'm keeping my eyes out for that. It's not there. Everything's a carbon. It's all good. Okay, now if we do it by analogy from what we've previously been doing, I would have used the negative charge on the sulfate to come in and attack the positive charge on the carbon. And that can actually happen if there's no water present. But there is water present, and there's a lot of water. And because there's a lot of water, water's going to win this race. Like, this guy might be the faster runner, but there's 10,000 water molecules, and they've got nasty elbows. And if you've ever run competitive cross country, nasty elbows get you a long way. I was good with my elbows. So what we're going to do is we're going to use the water, which isn't as good a nucleophile, but there's just so much of it. And it's going to come in and do the attack. This is why you need to keep an eye on what's around the arrow. In the other cases, the solvents couldn't do anything. They weren't reactive. They were organic solvents. They were boring. Water, on the other hand, is not boring. If we follow along here, the water, in this case, we now have a neutral molecule attacking. It's the first time we've seen this. Keep track of your charges. And we have an oxygen that has a positive charge on it. Now, also for the first time, it matters if this comes in from the top or the bottom. And we saw that with the empty p orbital when I was showing the example with the orbitals, that the chloride could come in from the top or the bottom. The top p orbital, the bottom top lobe of the p orbital, the bottom lobe of the p orbital can do the same thing here. And for the first time, we have a product which is not the same if it comes in from the top or bottom, because this is an asymmetric carbon, and there's another asymmetric carbon. So the arrangement between these two intermediates here is that they are diastereomers. You have flipped one, but not all the stereocenters in the molecule. And so they are not enantiomers. You'd have to have flipped all of them. You'd have to have made this methyl go from top up to down. There's no chemistry happening there, so nothing could happen there. And they're definitely not the same molecule because one of those is a water down, one of them has a water up. But we're not done yet because our thing is still charged. We don't want it charged. I need you to get rid of that H+. You can use whatever you want. You could use the negatively charged sulfate, but in reality, what's probably going to do that for us is another water molecule, because as we know, sulfuric acid dissociates completely into water, and it does that to hydronium. And so when we do that, I just didn't bother. So, yeah, the H2SO4 gave us the H+. So it's acting as an acid catalyst. And where the H on a ring go, I just absorbed into the ring because I don't need to draw in all the H's if it's on carbon. So you can still have it there if you like. You know it's there. It's a CH2. Nothing is drawn, so it's got to be CH2. I just dropped it because I can save myself a little bit of space by not having to write it in. Similarly, over here, get the same thing happening. Note that I don't really care what happens to the hydronium. Couldn't care less. It can go off and do its thing. What I'm doing is I'm keeping track of the major organic compound. I'm not trying to balance these reactions. I'm not worrying about the sulfate. The sulfate was here. I've lost interest in it. I'm now really focusing on what's happening to the thing with the carbons on it. I'm going to try and keep track of the byproducts on things and the side things that are being formed, but I know I'm not going to. I know I'm going to miss some of those, and you can too, and that's okay. What you need to do is follow the main molecule, your reactant, as it becomes product. We don't really care what happens to the reagents. They come in, they go off, they do their thing. Once they've done their role in the mechanism, I might need to remember what's there because I might need it again, but I don't care about its fate. Because I forgot the two. I'm really sorry. Yeah, it wasn't hydroxide. It was OH2. I'm really sorry. I just forgot the two. Thank you for that. They're identical. Like they're mirror images. They're not mirror images because they're not enantiomers, but the processes are absolutely parallel. And what you'll get is a 50-50 mixture. You'll get a 1-to-1 ratio of these guys because you got absolutely equivalent chance of the water coming in from the top or the bottom. And if you're doing this on 1 mole, which would be 55 grams or so, then you have 10 to the 23 molecules. And statistical chance will make everything the same when you talk about that many molecules, right? Like that's a lot of molecules. Okay. So let's think about something kind of similar. I'm just going to change it a little bit. No, you don't normally need to draw both processes. You can normally okay, I'm gonna make a rule about this later. We'll come back to it. I'm gonna draw both for a little bit. When I was taught this, I was told you always had to show and an enantiomer. Uh, a lot of people forget to write and enantiomer or and diastereomer if you're making something like that. And that is a stupid way to lose marks. And so I'm not going to ask for that. You draw one. I'm going to trust that you know that you get the other one as well, unless I explicitly ask you to draw all the products. If I'm just asking for a mechanism, you just draw one. You don't need to draw both. It's a waste of your time. Okay, so let's think about this guy. We're going to do something a little bit different. Iodonium chloride. I have no idea if that exists. If it does, it probably blows shit up just because it'll react really violently with water. So it's going to react really violently with our poor little molecule here. Now, so far, we've been attacking H+. That made sense. It was a nice H+. It was good. There's no H+ here. What do I do? What do I do? And you start panicking. You start getting worried. Okay, remember why we attacked H+. It was because the bond was polarized. So let's think about that. You have an iodine-chlorine bond. Never seen one of those before, probably. How is that bond polarized? Okay. Which of those atoms is more electronegative? Sweet. We got some chlorides in the chat. Amazing. Okay, chlorine's more electronegative. Chlorine, that I'm not saying it stabilizes a negative charge better, because it doesn't. Iodine stabilizes a negative charge better. But if you stick 2 electrons and you force chlorine and iodine to share them, chlorine's going to say, mine. And it's going to pull those electrons towards it, mine. And mine. Like the seagulls in Finding Nemo. And so it polarizes that bond. And that bond polarization parallels electronegativity. Now, it's only when that bond is formed. If I'm actually asking which is more stable, I minus or Cl minus, we did this with the acids, I minus is more stable. But when there's a bond between them, the chlorine is pulling the electrons towards it because it's more electronegative. Okay, now this is exactly the same as what we saw with H+. Iodine even looks a bit like H, just like an H on its side, right? Now I'm going to lie. I'm going to say it's exactly the same, and it's not quite exactly the same. So why did I draw that? Why does a positive charge go on that carbon? Exactly. Andrew says away from fluorine. You got inductive effects from the CF3. The fluorines are pulling electrons away from that carbon. It makes the carbon they're attached to slightly positive. This guy, this carbon itself is slightly positive. You don't want that next to another positive charge. That's bad. and a chloride comes in. We are at 218. I'm going to leave this there, and I'm going to say not the whole story. Because I've drawn one product. You do not get that molecule. So chlorine is coming in from one side of this molecule and not the other. And next class, we're going to take up why that happens. So we're going to pick up right where we left off right here. So I'm going to post these notes. I'll give them the date, but they're going to flow into the next one. I think Newman, but close. Whatever. Newton probably should have it named after him. And no. Sort of. Nope. It's a good guess, but no, there's free rotation theoretically around that bond. I've drawn something wrong here. I've lied a little. And we'll correct that lie. But if you want to think about that, go ahead. If you want to look it up in a textbook so you can figure out why I lied, that's cool too. If we had more time, I'd solve this, but right now I don't want to go over. So yeah, everyone have a nice weekend. Enjoy. It's 20 degrees out there right now or something. So it's a good time to go frolic in the backyard, socially distanced with your cats. Yeah, it's always time to frolic. Okay. Or if it's storming, I guess don't frolic. Okay, wonderful. Take it easy, people. Have a good one. No, wrong screen. There we go.